modeling IoT solutions falls into a specialized domain that requires a tailored modeling approach. To meet such requirements, we have developed an IoT-PML UML profile introducing a set of modeling constructs using MDG technology to deploy the UML profile with other extension mechanisms as a modeling framework enabling you rapid modeling of IoT nodes. MDG technologies allow users to extend Enterprise Architect's modeling capabilities to specific domains and notations. MDG technologies seamlessly plug into Enterprise Architect to provide additional toolboxes, diagrams, UML profiles, shape scripts, patterns, tagged values, and other modeling resources. The deployed technology automatically generates a list of elements and relationships in the diagram toolbox for each of the diagrams within the technology. Now, let me demonstrate how to use the IoT modeling framework in Enterprise Architect to model a smart thermostat. Our imaginary smart thermostat is a thermostat that can be used with home automation and is responsible for controlling a home's heating. Like a connected thermostat, it is connected to the internet. Therefore, it allows users to adjust heating settings from other internet-connected devices, such as a laptop or smartphones. Before I start modeling, I have to make sure that the MDG technology for IoT-PML is enabled. So let me check that. Specialize MDG technologies, and here it is. Perfect. Okay. Just like any other projects, even our project will start with specifying functional requirements depicting high-level functionality expected to be performed by our smart thermostat. For that, I will use a simplified version of a use case diagram also available in the IoT-PML modeling framework. Let me create a boundary representing our system, so smart thermostat. As a second step, you need to identify actors interacting with your smart thermostat. I identified that there will be some user, right? User using our thermostat. Then I realized that there must be some control unit. Please note that all these actors are coming from the defined meta model for IoT-PML. Therefore, in the toolbox you see only those relevant elements which are representing the modeling constructs of this particular diagram. So, the second control unit, let's say that would be boiler controller, and another one, since we are developing an IoT solution, so there would be a service. So the service, let's call it smart thermostat cloud. Okay, so as a first use case, I guess that would be the change temperature set point. And we will use to connect the particular actor with the use case, we will use the relationship association. Well, let's speed up the process and I will show you how such a use case diagram can look like eventually. So here it is. This is an example of a use case diagram for our smart thermostat, which shows the high-level functional requirements depicted as a use case diagram. Okay, the next step, what we are going to do, we are going to create a context, system context of our thermostat, and we will use a diagram which is specifically designed to do that. Okay, the system context is a high-level diagram which is going to reuse the already identified actors previously done in the use case model. And we will identify the information being sent to the system or sent out of the system towards the external entities. So the first thing, we have a special element, stereotype system, which represent our smart thermostat. And as I already mentioned, we will very elegantly just reuse already existing elements, this time as a link, select for all. And here we go. We have all the elements already available here. I will just get rid of the namespace. Okay, and the second step, what we are going to do, as I already said before, we are going to use the information flow, which will define the information being conveyed, in our case from a user towards the thermostat. So I'm going to show you just one example, and again I will speed it up the whole process, and eventually I will show you the final look of the system context, how it could look like. So in order to add information item, I will select new, context, and in this case we are going to use information item, and this information item will be called user commands. Okay, and there you go. Here we go. Here is the final appearance of the system context. So let me just quickly walk through that. So we already, in the first place, we just define user commands, sending from the user, then I just added set points, and then our thermostat is sending back towards the user required temperature value and system information. Then towards the boiler controller, we have some equipment operation commands, and the boiler sends back to the smart thermostat a boiler water temperature. Smart thermostat cloud, that's the cloud service. It receives from the smart thermostat occupancy status, required temperature value, and application firmware, equipment operation commands, and set points is sent back towards the smart thermostat from the cloud. Okay, what is also recommended when it comes to the grouping all these information items, the good practice is to group them into package. So I just call it information items. If you will, you can call it external information items. It's up to you. Just for information, we are not going to model the whole thing, and that's just hypothetical example how to use the framework, not to build a smart thermostat. So please just bear with me, and we can continue right after the system context by developing or creating a decomposition, where the next step where we will decompose the smart thermostat into a system components, and that's slightly touching already the IoT-PML. Okay, so for that I will create one more package, system decomposition, and we have a specially developed diagram for that as well. We will just drag and drop this smart thermostat. By the way, I just noticed that the system decomposition should be at this level, so I just move it to the level of views. Okay, so here we are reusing again the smart thermostat. I will get rid of the show namespaces, and as the toolbox items suggest, we will create in the first iteration something called system components. So the procedure is as follows. So we will create so many system components, as many we identify that they are needed to get our smart thermostat functioning. Okay, so let's say the first component is definitely going to be HMI. So that's the first iteration. In our case, it's obvious because both will be realized by hardware. So, but if you identified some system component which you are still not sure how this is going to be realized, whether it's going to be realized by software or hardware component, then you can leave it as a system component and then later decide what it is. I will just show you how to transform the system component into a concrete, whether it's hardware or software. So I will use the hardware component and I will place it onto the already existing system component, in our case HMI, and I will, EA asks you whether you want to convert it or add as a new one. So in my case, I will select convert, and here we go. The icon has changed accordingly, and now we have, if we look at a stereotype, we have IoT-PML, stereotype hardware component, which is a type system component. How cool is that? Oops, I wanted to select the hardware. Okay, convert. Here we go. Again, I will speed up the whole procedure to make it complete. And here we go. This is the result of our smart thermostat decomposition. So let me quickly walk through that. So at the highest level, our smart thermostat is comprised of housing, mainboard, and HDMI. Then the mainboard, the PCB, is composed of all these hardware components. And just to point out the difference between a hardware component and a software component, we did identify two software components which are running on this microcontroller, such as application and a bootloader. Okay, so first iteration of our system decomposition is behind us. Now let's have a look how we can add interfaces to the identified system components. So first I will quickly show you the principle how you would build such a diagram, and then I will show you the final state, how the diagram could look like for real. Okay, so how would you create such a diagram for system interfaces? Again, you would use the system decomposition diagram, but this time you would call it system interfaces. And as a first step, what you would do, you would say, okay, I'm going to use, for our sake, I'm going to reuse just the radio chipset and mainboard. I just copied those elements from the previously created diagram and paste it onto the newly created one. And here is the cool thing. In order to show nesting, visually show nesting, what we can do, we can just drag and drop this element onto the nesting element, and the comprised relationship will automatically disappear because EA will recognize, hey, this is in fact the same meaning. Okay, so normally what you would do, you would just recreate the nesting according to the reality based on a system decomposition. In our case, as I already said, I will show you how to assign perhaps some new interfaces to the radio chipset and how we would work with the interaction. First step, you would create some interface. The interface, I just opened the already existing diagram. Again, the diagram is the same diagram type, system decomposition diagram type, like you would use for the previous diagrams. And you would just use this item from the toolbox in order to create a new interface. Since we already have some interfaces defined here, I'm going to reuse this interface. I think I selected the radio chipset, so the radio chipset will use some digital interface. Now let me show you how you can assign this digital interface into this component. Okay, so what we will do, we will use the expose interface element, and by double clicking and selecting the three dots, we will find the identified interface declaration, which will be exposed by this exposed interface element. Here we can decide whether it's going to be the lollipop or the socket type. In our case, it's going to be provided interface, and it automatically used the name after the system interface declaration. So that's a first step. So we just identified an interface and exposed the interface for the component, hardware component, which is within the main board. I just realized one thing, this doesn't belong here. Oops. Anyway, okay, so as a next step for the main board, because we don't know what exactly this is going to be, what kind of socket or what we are going to use at this point. That's why we just will use the interaction point for the main board, and the interaction point will be, in this case, some antenna. So here we go, we have an antenna, and here we will simply just select the digital using the connector relationship with the antenna. Okay, just to keep track between our system under design and the external entities, we need to have some external entity, right? So in this case, we would use the smart thermostat cloud. Again, the same exercise, Control C and Control V to copy a link of the existing element onto the newly created diagram. And here, what we will do, we will assign the information flow, and we will select the already existing information items, which will be conveyed from the from the radio chipset towards the smart thermostat cloud. So if we just if we looked at the system context, we would know that that would be the occupancy status and the required temperature value. So what we can do, it's also a good practice to visualize those two diagrams next to each other, so you get the idea. So okay, so there will be this one, and information flow from here to the radio chipset, and there will be application firmware and equipment operation commands and set points. So in fact, we are now modeling this part of the system context. To make the interaction point bigger, you have the option to go to the context menu, advanced, and port size customized, and you can change the size of the port to make it nicer, just like that. Okay, so we'll close the system context. So these are the steps necessary to build something like a system interfaces. I just realized I made a typo, but the typo will actually help me, because now I will show you how the system interfaces can look like when you finish the whole work by using the the steps what I showed you. So here it is. This is our radio chipset. So that's how the system interfaces diagram can look like. So again, we reuse the already existing system components, and we just added the exposed interfaces elements and interaction point to the external parts of the system, representing perhaps some hardware interfaces. Okay, so that's how it looks like. So we can just go through it, not necessarily to explain. Again, this is a hypothetical situation, so I don't know how whether it really works like that, but this is just an example how it could work, the smart thermostat. Okay, system interfaces done. If you another best practice, what you can do when you model the system decomposition at this level, you can also reuse these elements, and you can model behavior using sequence diagram, and the result could look like this. This is amazing. So you just reuse the already existing elements, temperature sensor, microcontroller, and you can make visible also the embedded elements, such as the ports. In our situation, that's interaction point and the exposed interfaces. And here you see how it communicates between each component. Again, this is a very, very high level. And now let's have a look how to model a software stack, which is the main part of the IoT-PML. All right, so for that, I will create a new package at the highest level, and I will call it software stack. I will keep the option create diagram. Okay, and here I will select the customized diagram provided by the framework, which has the same name, software stack. Okay, I can change the order just to make it more in a chronological order, and I will open the software stack. Now the software stack, this is a specialty for the software stack, and the implementation of IoT-PML in Enterprise Architect will help you to generate the model structure in the first place. What you do in the software stack, you can decide what layer you are going to model, because not always all the layers are necessary to model. So in our case, I will just show you some example how to model application layer and how to build the structure using something called the patterns, and then I think you get the idea how to use it. So I will just create the application layer, and the layer will be called application. Okay, so it automatically created a package, and here I will use the patterns. I will create one more time diagram under the newly created layer, application layer, and I will use the pattern for application layer structure, which will automatically create those three packages named interface repository, implementation, and a design repository. The first thing what you need to do in order to create the application layer, you will create a new diagram under the interface repository. The diagram will be also a software stack. And in the software stack, what you need to do, you need to create an interface which will represent a concrete software interface. So we can say there will be some interface events, and the interface events will have some behaviors, and the behavior will be get event. You can select the type. I will keep it integer. As you already know from the meta model, the behavior is in fact a special operation which is stereotyped behavior. So that's for the IoT, that's a part of the IoT-PML definition. So then you would just continue and you would identify the rest of the interfaces needed. The second step, what you would do for the sake of creating the application layer is you would create another diagram in the implementation repository, and in the implementation repository what you would do, you need to define or identify software components, in our case, because we are talking about application, which the software components will use some type of the interface. In order to keep traceability with the work what we did before, is to reuse the identified software component from the system decomposition and we can reuse and we can build also the hierarchy just like that. So that's the idea. You might be wondering, where are these operations coming from? Well, we kind of skip that, but those operations were already identified in a system decomposition in our case. So okay, coming back to the newly created system component, which we didn't give it a name. So let's say that the component will be event handler, and we are supposed to create a relationship, whether it's using or implementing this interface. So therefore we have this relationship usage, or if there was another interface, then we would use implement and then we would use the realization, and that would mean that this interface is implemented by the particular software component. Let us assume that we identified or we finished the implementation repository, and as a last step what you do, you create a design, you create in the design repository a design of this implementation repository. Okay, so again, first step, we will create one more diagram of the same type, and this time we are going to create an instances of the existing software components coming from the implementation repository. So this applies only for the design. It's for the case that sometimes we need to use multiple times of the software components or even hardware components if we are building a hardware abstraction layer. So there can be a case when we need to use multiple times the concrete element, and using the instance we can do that. Okay, we use the instance of the implementation of the software component stored in the implementation repository, and it's of the same type. We don't need to specify any type of the or any name of the newly created instance. And what we just need to do, the same steps. We need to expose the interface which is already identified in a previous work. So that's the events. Okay. And perhaps if we had another software component, then you would use the relationship use between those two elements. So let me just quickly show you how that would look like. I'm going to make a nonsense, of course, but just for the sake of showing you how possibly you could create it. So here is event handler. So you can, this is the situation when you can use one element more than 2 times, because we created instances of the element from the implementation repository. And this time what we can do, this event handler is providing the interface events, and then eventually we can just use it like that. And that's it. That would be it for the application layer. As I mentioned earlier, in a similar structure, what you would do is the hardware abstraction layer. So you would call it whole, and the same thing under that. You would create a new diagram, and then you would use the pattern for the hardware structure, which would create all those 3 packages: hardware design, hardware interfaces, and hardware implementation. Okay. In hardware, that's a specific layer, because in hardware you would use, especially in the implementation repository, you would use hardware components, and this is the place where you model the IP exact definition. So you can either import the IP exact XML, which would create structure similarly looking like this. You would have some register, you would have some field, and the register system components is comprised, and then the register is can be also comprised of some fields. And there can be another field which this main hardware component can be comprised of. Every element, such as register and field, has its own specified tagged values. So here are the options. So in case of register, you can define offset, base address, the width. In case of field, you can define the access, read only, and so on and so forth, the concrete value, base address, and also the width of the system component. What I haven't mentioned yet, every system component, whether it's hardware or software, can have references to either file or URI. Okay, another thing what you can do, another part of the IoT-PML is to define behavior specification of each system component. So let me just show you how you would do that. Okay, I just selected in the browser the software component event handler, and I will create a sub-diagram underneath the element, which will be type behavior specification. This specific diagram will allow us to create at the highest level behavior specification, which is a representation of an activity. And this activity we can model directly in this diagram using the specially defined toolbox. So first it starts with some initiation. Then we can define whether it's just a regular atomic action, or we can also define that it's call operation. In case if it's a call operation, we can define the behavior by assigning the operation to already existing behavior of the concrete interface. That's what we already did. So this is a nice traceability, the behavior definition to the static structure stereotype as a behavior, and now I will assign it to this operation called behavior of this behavior specification. So I can say another control flow. Here I will create one more action, which will be atomic, and I will just finish it off by defining the final. So then when we have defining the behavior specification finished, then what we can do, we can assign or stereotype the already existing elements by the control points. The control point is the point which we are interested in case of doing some measurements. Okay, so I just selected a control point from the toolbox, and I can apply control point stereotype to this existing action. Then the second thing what you would do, you would use the NFQ duration type, and here you have the option to either define that the constraint type is a constant value or value triple defined by max, min, and average point. So I will say constant value. And the kind is very important because the kind defines whether the non-functional quality property is description. So it's already measured value, or if it's required value. And the source can define a concrete string, how you measured, or the method how you measured the value what you already got. So you can use the NFQ for both, for defining non-functional qualities, or you can already use it to store the measured values back into the model. Okay, that will be it. And then you just define the start point by using the concrete relationship type start and stop from the toolbox, and the endpoint to identify the measurements. In a similar fashion, you can also NFQs assign to structure elements. So let me show you how to do that. So I can go to implementation repository, and we can say that this event handler, we have the NFQs already ready here. The NFQ can be memory type or power. In this case, so that would be, for instance, a memory. So we would say, again, the memory has this type, as we already discussed. And the memory can have, for instance, the footprint cannot exceed, I don't know if it makes sense, but that's what you can do. And simply you can just assign by using the trace this NFQ to this component that also keeps you a track. So this perhaps this is a kind requirement. So this is required that this component should not exceed the given footprint. You can also make visible the nodes. So you got the idea directly from the diagram. And another step what you can perhaps do with your system is to perform threat modeling. This framework also allows you to do that. Let me show you very quickly how you can create a threat model. So for that I will create one more package and I will call it threat model, keeping the selection create diagram, and I will select the threat model, which is also part of the whole framework. Okay, so this is the threat model. We can just, I can change it because I will do the context level, context threat model. The context threat model, as the name suggests, that's the highest level what you can do. In this case, I'm going to reuse these elements what we already have to start with. So we have these external entities defined, and then the next step in the as a part of the threat model, you have to define the classic data flow diagram using these elements such as data store, process, and data flow. So very simply drag and drop all these elements onto a diagram, and then use a data flow which defines how the data is flowing. So data storage goes here, for instance, and so on and so forth. I will use the trick one more time to show you the final result, how your threat model can look like. Voila! So this is the result of the threat model of our imaginary smart thermostat. So hopefully you enjoyed the video, and happy modeling with our IoT-PML framework.